The word phase is synonymous with state of matter. So when they say a change of phase, we really mean a change of state. So from solid to liquid to gas. And when we're talking about phase separation, which is what this topic is all about, it's really how can we separate mixtures? And when we do separate these mixtures, we sometimes have to change their state so that we can separate one component from another. So what are mixtures? Well, they are impure substances, meaning they have more than one types of compounds mixed together. Now, they are not mixed chemically, they are mixed um, they are mixed physically. So, for example, if you have alcohol mixed with water, the alcohol is not really bonding with the water molecules and changing the chemical composition. It's just mixing together um, with with the molecules are just in the same container together. So, how can we separate these mixtures? Well, you have various ways to separate it. You have simple distillation, that should be fractional distillation, vacuum distillation, steam distillation, solvent extraction, and the use of a separating funnel. We're going to go into details with some of these right now. Before we do that, though, we have to understand the idea of vapor pressure. Now, if you have a container that is shown on the screen like this, you will have the liquid in the container, but after a while, some of the liquid molecules that are at the surface of the liquid, they are going to escape the liquid phase and go into the gas phase or the vapor phase. And again, some of the molecules in the gas phase, they're going to go back to the liquid phase and it's going to keep going like that. And eventually it's going to get to a state of equilibrium, meaning that the molecules going from liquid to gas and gas to liquid, the rate at which they change is going to be more or less the same, and they're just going back and forth. So when that happens, the molecules that are gases they are going to exert a sort of pressure in the container, and we call that pressure vapor pressure. Now, if you increase the temperature, you are going to change the pressure, the vapor pressure. And if you have a mixture, so if you have two liquids instead of one, then each component is going to do the same thing. So say, for example, you have ethanol and water. The water molecules are going to change the vapor, and the ethanol molecules are going to change the vapor. And so those vapor molecules are going to exert a pressure of their own, and we call that partial vapor pressure. Is that clear so far?
Yes, miss.
I'm going to show you a quick animation of what exactly that looks like so that you can see what I'm talking about in real life. So basically, these things are happening. We can't really see them, but we can understand how they work based on um, the, the different movement of the molecules. So as you can see here, you have a container with a substance A and a container here with a liquid B. And the molecules, they are escaping and they're becoming gases, gas molecules that are above the surface of the liquid, and you have the liquid here. And the same thing is for liquid B here. Now, when you mix A and B, if you notice now, you are going to have a pressure that is exerted by particles A and one that is exerted by particles B. And so you will have a different kind of pressure, vapor pressure, for the mixture itself. Okay, so that's what's really happening here. Now, how do you find the total pressure? How would you find the total pressure exerted by the molecules here? What do you think you could do to find the total pressure of the molecules, the vapor molecules that are in this mixture in component A and B? How do you think you would find it?
Miss, you're not going to use the constant?
Well, it's simpler than that. We'll get to a constant shortly, but it's simpler than that. All you would do is add up the partial pressures, right? So if A and B are both in the container, you would add up the pressure of A and then add and then get the pressure of B and add them together to get the total pressure. Does that make sense?
Yes, miss.
Yeah. So it's quite simple. So that is what vapor pressure is. Again, vapor pressure is the pressure exerted by the vapor molecules when they're in a container, a closed container in a state of equilibrium like this. Okay? Now, if it's a mixture, you will have a partial vapor pressure exerted by one molecule and a partial vapor pressure exerted by another molecule. Now, there was this Frenchman way in the 18 and 1900s called Francois-Marie Rolle. I don't know if that's exactly how you say his name, but something like that. And Rolle, he realized that if you mix liquids together, you can tell something about their pressure. So he recognize that if the forces of the intermolecular forces in the molecules are the same as the intermolecular forces of the individual molecules, if they are the same after you mix them, then the total pressure of the mixture is going to be equal to the sum of the vapor pressures of each component. So that's what I was just showing you in the video. If you wanted to find the total pressure of the mixture, you would just take the pressure for the component A and the pressure for component B, and you would add them, right? Then you would have to also multiply by the mole fraction. Now, the reason you're doing this is because the number of moles in A and B will have an effect on the pressure that they are exerting in the container. So, this was what I just pulled from one of the Cape Chemistry books. And it's basically saying the same thing that we just said and demonstrated in the video. So the liquid in a closed container is going to have vapor, and those vapor particles are going to exert a pressure. And the liquid and the vapor particles will be in a state of equilibrium. So this is again saying the same thing. You have the liquid particles here and they're constantly moving to become vapor, and the vapor particles are moving to become liquid. And remember, the container must be closed because if the particles become vapor and they are allowed to leave, then you won't have a pressure exerted on the system. Again, that is just saying the same thing again, just to reiterate and make sure that we understand. So again, Rolle's law states that if you have two liquids that are miscible, meaning that they can mix together, then the total pressure is going to be the partial pressure of A plus the partial pressure of B. How do you calculate the partial pressure? Well, partial pressure is going to be equal to, the total pressure, sorry, is going to be equal to the partial pressure multiplied by the mole fraction. How do you get mole fraction? Well, you take the number of moles of A and you divide it by the total number of moles. And you take the number of moles of B and you divide that by the total number of moles. So that is the mole fraction. So to get the partial pressure, it's going to be A, the partial pressure of A times the mole fraction, and for B, it's the partial pressure of B times the mole fraction. That's how you get the vapor pressure. So let us now talk about the difference between miscible and immiscible. Have you ever heard those terms before? And what do they mean?
Miss said they're able to dissolve.
Yes. Miscible means that they can dissolve and mix together to produce a solution, while immiscible mean they cannot mix together. So an example of a miscible liquid would be syrup and water, ethanol and water, easily mixed, and you get a good solution. While an immiscible liquid would be oil and water, hexane and water. Anything oily with water, they don't mix together. They form a separate layer, right? The oil is going to float on the top and the water at the bottom, right? So those are immiscible liquids. All right. In the interest of time, I'm going to skip this video and we're going to just reiterate what we said about Rawls' law. He said that if the partial pressure of a component in a mixture is equal to the mole fraction multiplied by the vapor pressure. So again, partial vapor pressure of A is going to be the vapor pressure multiplied by the mole fraction. And partial pressure of B would be the vapor pressure of B multiplied by the mole fraction. And the total pressure would be A plus B. So it would be the partial pressure times the mole fraction of A plus the partial pressure times the mole fraction of B. How do you find mole fraction? You take the number of moles of A and you divide it by the total number of moles. Okay, so mole fraction would be equal to the number of moles of A divided by the total number of moles, which would be number of moles of A plus the number of moles of B. Okay, so that is mole fraction. That would be XA. Okay, so that's Rawls' law. Now, this total, when you're adding the partial pressure of A and the partial vapor pressure of B to get the total pressure, that is under ideal conditions, and we call that the ideal mixture. So basically, if a mixture is ideal, certain things must occur in the mixture. The intermolecular forces between the molecules in the mixture are similar to those of the pure substances. So let me explain. Suppose you have a substance A and you have a substance B. If the intermolecular forces inside A are van der Waals forces, and the intermolecular forces in substance B are van der Waals forces, and when you mix them together, A plus B, it's not really a reaction, so I'm going to put A plus B again. When you mix them together, you are going to, when they come together, you still have the same van der Waals forces, then that means that that mixture is ideal. The next thing that is good about ideal solutions, if there are no enthalpy or volume changes on mixing. Did you know that sometimes when you mix two substances together, it can change the volume? For example, I want you to try it at home. Take some water I'll fill a glass all the way to the top. And then I want you to take like a big teaspoon. I don't want to know waste out on a parent salt, but if you want to try, take a big spoon of salt and place it into the water. What do you think will happen? Will the water overflow the glass? If the water was already at the top and then you put salt, will it overflow the glass? What do you think? Hello?
Miss, I think the salt reacts with the water, so maybe not.
Sorry, say that again.
The salt would react with some water, so maybe not.
No, it won't react, it will dissolve, right? React would mean like it would change into something other than salt, but it's not gonna react, it's gonna dissolve, and actually it's gonna overflow because the volume is going to slightly change when you add water. So if that does not happen for a mixture, then you say that the mixture is ideal. Now I'm going to show you a graph of what happens when you mix hexane and heptane. Hexane and heptane. Now, as the mole fraction of the more volatile component, that means the one that produces more vapor and have more vapor pressure, then, which is the hexane in this case, the partial pressure of the more volatile component is going to increase, and the partial pressure of the less volatile component is going to decrease. So the total pressure overall increases so that at any point, the sum of the partial pressures is equal to the total pressure. So let me show you that on this graph. Now, interestingly, if you do mathematics, you are going to come across this type of graph. But just because this is not a math class, I'm going to try to make this as simple as possible. Now, if you take a look at this axis here, which I'm drawing this arrow to point at, this is an axis that is showing the vapor pressure of heptane, and this axis here shows the mole fraction, Now, they also are trying to show you the relationship between heptane and hexane. So they drew a second axis on this side. And so you have one axis going like this, and then the other going like this. And then you have one going like that. Change color here. And coming down and meeting with the same y-axis, okay? Now, what they did is they plotted a graph of the vapor pressure of heptane against the mole fraction. Now, that is what you are seeing here. This is going to be, I'm going to keep the colors so that we can keep it straight. This is the vapor pressure against the mole fraction. So if we're taking a look at just this red line here, what is happening? It's telling us that the heptane started with a relatively high vapor pressure, and as the number of moles or the mole fraction increased for heptane, the pressure decreased. Okay, I hope you can see that. Now, for the second relationship, which is hexane, it is a more volatile liquid. So its vapor pressure is higher. Its vapor pressure is higher. That means it has more gases coming off of the surface of the liquid. And again, if you notice here, the same thing as you increase the mole fraction for this one, as you increase the mole fraction, the vapor pressure increased, okay? So that is the composition curve. Now, because as was said here, the total pressure, because the partial pressure of the more volatile component increases and the partial pressure of the less volatile component decreases. So let me show you that again. If you look at what is happening for hexane, it starts off here and it's increasing. And if you look at what's happening for heptane, it starts off here and it's decreasing. Okay, so one is increasing and the other is decreasing. So they have an inverse proportional relationship. So what happens then is that if you were to add them up at any point, so let me just show you that at any point, if you were to say, okay, what is the, if you take this small fraction here, let me see where, with both, okay. If you take this small fraction here, and you were to see what the partial pressure is of heptane, which would be somewhere around here, and you take the same mole fraction and see what the partial pressure is, which is somewhere around here, for hexane, right, which is a more volatile liquid, the total pressure would be somewhere around here for both of them. So the total pressure, because one is increasing and one is decreasing, you are going to be getting the addition of both numbers at the same time. So this number here plus this number here should give you this number here. Okay, so the partial pressure of one of them plus the partial pressure of the second one is going to give you the total pressure. All right, now when we are doing experiments, if we are going to carry out an experiment, it's hard to find the vapor pressure. And so using the boiling point to see the relationship between the molecules, which one is more volatile and which one is less volatile, is ideal. That is the best way to show that experimentally. And you can still see a linear relationship between the mole fraction. So if you look at the boiling point, for heptane, it has a higher boiling point when you're comparing it to the number of moles. And for hexane, it has a lower boiling point with the same number of moles. So you can see here that the more volatile liquid has a lower boiling point. So this one, if you were to boil the two of them together, this one would evaporate first, the pure hexane. And you can see that here as well, the hexane is more volatile because it has a higher pressure, okay? I'm gonna erase this when I send you the slide so it's not very confusing. All right, so the boiling point, the lower the boiling point, the more volatile it is. That means that it is going to have a greater vapor pressure. Now, some mixtures do not obey Raoult's law. This means that they do not increase the relationship between the vapor pressure or the boiling point and the mole fraction is not really linear. It's not in a straight line like you saw in the other graph. So you can have a positive deviation from Raoult's law or you can have a negative deviation from Raoult's law. Now, let us look at a mixture of ethanol and cyclohexane. Now, ethanol and cyclohexane, the bonding in ethanol and cyclohexane is weaker than the bonding between ethanol alone and cyclohexane alone. In cyclohexane, the molecules in ethanol have hydrogen bonding, and the molecules in cyclohexane have van der Waals forces. Now, when you mix them together, the cyclohexane just come and get in the way of the hydrogen bonding, and so it causes those hydrogen bonding that were in the ethanol at first to break. And as a result of that, the mixture is more likely to escape into vapor, and it will have a higher vapor pressure than the ethanol alone or the cyclohexane alone, because you have a lot of bond breaking there. So the vapor pressure of the mixture is higher than you would expect for an ideal mixture, because it's not exactly the sum of the partial pressures of both of them, but because of that additional information about the hydrogen bonding, it tells us that the mixture is going to have a lower boiling point than you would expect. So that is a positive deviation from Raoult's law. So let us look at what is happening here. You have the pure ethanol and the cyclohexane, and if you were to obey Raoult's law, you would see a straight line here, a linear relationship, where the vapor pressure of the ethanol is higher than the vapor pressure of the cyclohexane. Now, what you actually see is that the pressure of the mixture is it's giving this slight little curve here, so it's not exactly linear, and the vapor pressure of the ethanol is slightly higher than you would expect. Now, the same thing here for the boiling point. If you notice here, the boiling point of the mixture is going to be slightly lower than you would expect because of the hydrogen bonds that are breaking in the ethanol. So you get a lower boiling point for your mixture. Now, what about negative deviations from Raoult's law? If you mix ethyl ethanoate and trichloromethane, the bonding again between the ethyl ethanoate and trichloromethane is actually stronger. So what is happening is when you try to boil that mixture, the boiling point is higher than you would expect. And as a result of that, you have a lower vapor pressure because less molecules are escaping. So you notice this is the ideal with the straight line here, and you have a lower vapor pressure with comparison to the mole fraction than you would expect. And as a result, that would give you a higher boiling point than you would expect when you mix those two together. So we're going to cut off in just a moment. So I want you to rejoin, please, and then we will continue.